All right. Feels like it's been a long time since we had a class, doesn't it? But all right, anyway, so let's go back and see where we left off. We were part of the way through chapter 3, which, hold on one second, let me go get Moodle open. Okay, so anyway, here's what happened. Now, if you notice that chapter 1 is broken up into parts 1A and B and C. Chapter 2 is the same thing. Now, chapter 3, when I posted it, I thought it was completely finished, and then I realized after the fact that there were some topics that were still not there. So what I did was, rather than rename them, what I did was I posted today something that I'm calling the chapter 3 appendix. So instead of having, in this case, chapters 3A and B, which is what I would normally do, since I messed up, I'll just leave this chapter 3 with the same name. And then the remaining few topics are included in this the chapter 3 appendix. So by the time we're done today, we should be completely done with 3. And we should also have at least started the appendix. Okay, some of the topics in chapter 3 appendix are very straightforward, and 1 or 2 of them are actually quite messy. So we'll see how that goes. All right, but in the meantime, what I'd like to do is quickly go back and revisit some of these topics that we looked at the other day, by which I specifically mean chapter 3, the rules of differentiation. We went through a lot of theory. We showed how derivatives are defined in terms of limits, which is important, but going forward, it's not likely that we'll ever actually do this again. Instead, we'll focus on the rules. And so we saw that there are several rules that we can use. There's a couple of others that we haven't quite gotten to. So if you look at the chart that I put in here, okay, where is it? Here we go. All right, so we have the constant rule, the power rule, the rule for sums and differences, the product rule, and the quotient rule. We haven't quite gotten around yet to the generalized power rule or the chain rule. We saved those for last because they're more involved. In fact, in the book, the chain rule, they actually saved it for much later. But at some point, we'll be using it quite regularly. In fact, it will show up all the time when you come right down to it. It's very, very powerful, and just knowing this rule makes it a lot simpler for us to calculate derivatives. So just a quick review of these rules. The constant rule is particularly simple. Anytime you have a function which consists of a constant, then the derivative is just 0. And of course, the reason for that is because the derivative is a rate of change, and if the function is a constant, then no change is going to take place. And so it makes sense then that the derivative will just be 0. Now, the power rule, this is something we're going to see quite often. Even if a function is more complicated than this, often it can be decomposed into several terms, some of which at least can be calculated with the power rule. So just in general, as long as we have a constant being multiplied by x to the n power, where n is some real number, although in these examples, we've been restricting ourselves to integers, we'll see later on that that's not necessary. You can have any value for n you like. It can be a fraction, it could be pi, it could be almost anything you could imagine. But so far, we've focused our attention on integers. Once we have that established, the formal rule says that the derivative is n times k times x to the n minus 1 power. So essentially what you're doing is if you start with a function like 5x to the 4th, you're multiplying the entire expression by the exponent 4. The 5x doesn't change, and then the exponent of x is actually reduced by 1. So you're really only doing 2 things when you come right down to it. You're multiplying by the exponent n, and you're reducing the exponent by 1. So in this case, we ended up with 20x to the 3rd power. So we'll see quite a few of these. Like, for example, if you're evaluating a polynomial is itself just a series of terms that look exactly like this. So just as a quick example, let me just sneak a new one in here so we can see what that's all about. Hold on one second. Yeah, okay. Just want to make sure I'm in the right place. Let's just say that we had something like this. So this is a polynomial of order 5. The order simply means that the highest exponent is 5. So what if I need to know the derivative? Well, each of these first 3 terms can be evaluated with the power rule. The last term we can evaluate with the constant rule. So how would that work? Okay, so like this first term would be 5 times 4x to the 5 minus 1. Then we have minus 3 times 3, x to the 3 minus 1. Now, this one, remember, when you just have a constant multiplied by x, let me just put this over here. If f of x is simply kx, based on the power rule, remember there's an implicit 1 here. We'd have 1 times k times x to the 1 minus 1 power, which means kx to the 0, which of course is just 1. So f prime of x is just k. So this is a special case of the power rule. So the derivative of 2x is just 2. And then, of course, the derivative of any constant is 0. So the final result would be 20 x to the 4th minus 9x squared plus 2. And that's it. You're done. So you basically have applied the power rule 3 times and the constant rule once. So there will be many, many cases where you can do exactly that. After a while, it'll become second nature, as a matter of fact. You won't even have to think about the rules. You'll just go ahead and start doing them. But just be aware that what you're essentially doing here is applying the power rule to the first 3 terms, and then finally the constant rule to the last term. All right, so now, by the way, again, I did mention that the exponent does not have to be an integer. For example, if I have this one, x of x is 3 radical x, keeping in mind that radical x is x to the 1/2 power, the setup is exactly the same. But remember, since n is 1/2, what you're going to wind up with is 1/2 times 3 times x to the 1/2 minus 1. And of course, that means we have 3/2 x to the minus 1/2 power, which is fine. But if you want to rewrite it as a radical, just remember, a little reminder, this is the same as 1 over radical x. Okay, so we end up in that case with 3 over 2 radical x. All right, so now let's get to the trickier ones. How about sums and differences? Now, these are easy. It couldn't be any easier. All you're basically saying is that this derivative of a sum is equal to the sum of the individual derivatives. Okay, so these are very straightforward. So we can do this with sums. We can do these with differences. In fact, I'll tell you what, let's make up a new example right now, just to remind ourselves how this works. Okay, so now we can think of these as individual functions. If we choose to do so. It's not absolutely necessary, but this illustrates the rule. And so g prime of x, based on the power rule, would be 7 times 3 x to the 7 minus 1, or 21x to the 6th. H prime of x would be minus 6 times 5 x to the 6 minus 1. So based on the sum rule, actually, this is technically the difference rule, but because I've written this derivative as a negative, it doesn't actually make any difference. Any way you look at it, you're going to wind up with 21x to the 6th minus 30x. And that's all there is to it. So now we move on to the challenging ones. Like, oh God, this product rule, yes. Now, if you were taking this class in person, you would almost certainly have to memorize this. I can't imagine the calculus class where they would let you not memorize this. you might as well anyway. It's going to be so helpful to you in the future. If you're going to take more math, especially more calculus, it's the kind of thing you really should have it memorized. And so use whatever technique it takes. Everyone's memory works differently. Set up some kind of mnemonic device that helps you remember it, and plug it into your memory. And so essentially all you're seeing here is it's the first function times the derivative of the second, plus the second function times the derivative of the first. Okay, so let's take a look at an example. We had, and by the way, in a case like this, a very simple case, you do have the option of simply rewriting it. Like if you notice here, we could have just as easily multiplied this out and used the power rule. Okay, well, sometimes it works that way, sometimes it doesn't. Because clearly f of x could be rewritten as 6x to the fifth, and then you can use the power rule. But if you want to use the product rule, you have to evaluate the derivatives of both h of x and g of x. And so if the first term is g of x, the second is h of x, then g prime using the power rule ends up being 6x to the first, or just 6x. And on the next slide, I must have put, yeah, there it is. For h of x, 2x cubed ends up being 6x to the second power. And now we just use the rule. So I've summarized everything again here on this slide. We've got the g of x, the h of x, and the two derivatives. I've got the rule written right there. And so you plug everything in. And then once you plug everything in, sometimes you can simplify it, sometimes you can't. In this case, it was relatively straightforward, and we ended up with 30x to the fourth. Sometimes too, if you're using, let's say, trig functions, sometimes there's many identities there that you can use to speed things up a bit. Here, this is the best we can do. All right, let's see. Now the quotient rule. Now this one is a challenge. Okay, I'll give you that. It's a little bit messier, and of course we have to make sure that we did not accidentally introduce a function in the denominator that is equal to 0. So when you do have a ratio like this, this is how we solve for the derivative. Yeah, that's a lot of memorizing, but again, just do what you have to do to stick this into your memory. All right, so we have an example here. And once again, I mean, if you have a ratio that can be simplified, you can feel free to go ahead and do it. You may not even need to use this rule if it simplifies enough. Okay, and sometimes it does work out that way, like if you can factor or something. So, it's always a good idea to see if you can simplify any problems you're working on. And then that way you can use a more less complicated rule. But if not, you can just use the rule. So here's an example that we had. 3x squared minus x plus 1 over 4x cubed minus 3x squared. And there's really no way to simplify this. So we'll treat the numerator as g of x, the denominator is h of x. And again, you notice what we're doing here to come up with g prime of x. You're basically applying the power rule twice and the constant rule once. Down here with h of x, you're applying the power rule twice. So for g of prime of x, we ultimately end up with 6x to the minus 1. And for h prime of x, we ultimately end up with 12x squared minus 6x. Now we just plug everything in, and most likely we'll end up with a very messy result, which may or may not be simplifiable. So when we do that, let's see, what do we get? Okay, wow, that looks pretty scary. And you can just leave it like that. Unless there's a reason why you need to have it as simple as possible, unless you have reason to believe that you can actually find a way to simplify it a little. This is fine the way it is. All right, so now that with all that back fresh in your memories from a long layoff, Now we're going to look at the generalized power rule. So let me just quickly go back and grab the regular power rule, just so you can see the comparison between the two. Where is it? Okay, here we go. So this is what we were doing before. When we first introduced the power rule. So I'll sneak it over here, just a quick reminder how it looked before, and what the derivative was in that very basic case. Oops, hold on. Okay, so what's different now? By the way, you could have a K in here, it's possible, but what's really different now is that instead of having X raised to the nth power, it's been replaced by a function of X. Okay, so in other words, it's become a lot more complicated. And so the exponent part doesn't change. It's still n times the function to raise to the n minus 1 power. This is the new part. Whatever g of x is, we need now its derivative multiplied by n g of x to the n minus 1. That's the interesting part. This has a derivative. Now, up here, in principle, we were doing that. But because we had just plain old x to the n, whatever it was, we didn't need the derivative because it would have just been 1. Okay, so let's just take a look at some examples. So like here we go. Now you notice the difference. Instead of having something like this, f of x is 3x squared or something like that. All of a sudden, instead of x, we have this very messy expression. This is our g of x, okay? And it has its own derivative, which again, we can obtain by applying repeatedly the power rule and the constant rule. And that gives us 6x plus 4. And of course, over here, we have n is 3, because the general expression is g of x to the nth power. So what do we expect to get when we take the derivative? All right, so here again is the rule. And just quickly reminding you, this is the g of x. This is g prime of x. And since the exponent was 3, the 3 moves into the front, and the exponent up here is now n minus 1. So this is our final result. 3 times g of x, 3x squared plus 4x minus 1, raised to the second power. And then this piece, which we never had before, the derivative of what's inside the brackets is the new part, basically. That's interesting. And of course, it's more complicated. Okay, so we're going to see a lot of this, by the way. All right, so let me just make up a completely new one now. Let's say that you were confronted with this. Okay, so this is g of x. This is n. And so remember, this rule is oops. So we actually already have everything we need, except we don't yet have g prime of x. So again, since this is a polynomial, it's easy to do it because all we have to do is apply the power rule, the basic power rule, I guess we could call it, and the constant rule for each term. So we'll end up with 12. Actually, let me write it out like this. 3, 4x to the 3 minus 1, minus 2 times 3 times x to the 2 minus 1 plus 0. All right, and so based on this rule, the derivative must be 4, that was the original exponent, g of x, the original function, 4x cubed minus 3x squared plus 7 cubed, because it's n minus 1, and then we multiply that by g prime of x, 12x squared minus 6x. And we're done. Now, again, you may want to simplify it a little or do something with it. It's fine the way it is for our purposes, but there could, if you need, for example, to evaluate this at a specific constant, it's possible that you may want to simplify it, but it's fine the way it is. All right, so what we're going to do now is bring back a concept that we briefly mentioned, but we didn't really get very far with it. This notion of first, second, and third derivatives. In other words, the derivatives that we've been calculating actually are what we call first derivatives. You can always apply these rules as many times as you want. And, you know, in real world applications, we often do need the second derivative, which represents the rate of change of the first derivative. But ultimately, all we're doing is reapplying the same rules over and over and over again. Okay, and of course you can see, just like any other polynomial, all we're really doing is applying the power rule and the constant rule until we're done. All right. So what we're going to do now is actually apply all three of these. We're going to take the first, second, and third derivative of this expression. Okay, now, by the way, I wrote out in this next slide the general formulas for all three derivatives. You don't really have to memorize this or anything, just as long as you understand the rules, this will work just fine. Okay, so let me just quickly show that to you. So yeah, this is the one we know by heart. But if you notice, if we reapply the power rule, then we end up with n minus 1 coming down in the front times the existing values of nk, x to now to the n minus 2, because we've subtracted 1 from the exponent. And then for the third derivative, well, now we bring the n minus 2 down in front of n minus 1, nk, and then x is now to the n minus 3 power. So you don't have to really, like I said, you're not likely to just throw those formulas around. You're probably just going to use the techniques as many times as you need to. But it's good to see what this looks like. And then, of course, you can keep going as far as you can. And for the most part, at least any polynomial will eventually go to 0. You can only take so many derivatives. Some functions, that's not true. For sines and cosines, they'll just go on and on forever because the way they are structured. But most functions, eventually there comes a point where the derivative is 0. All right, so let's just do this. Let's just run through these. Here's the function again. The first derivative we'll calculate the way we've been used to. You'll see there that we apply the power rule to each of the 4 terms in the normal way. The 10, of course, drops out. And you can see that the first derivative ultimately turns out to be 20x to the 4th plus 12x cubed minus 15x squared plus 7. And so it's still a polynomial. So I'll give you a minute to catch up, and then we'll do the second derivative. In fact, you may want to go ahead and get started on it. Just remember, you're just applying the power rule to the first three terms here, and then the constant rule to the 7. And when you're done, you'll end up with the second derivative, which is, by the way, expressed as f double prime. All right. So let's do it. All right, let's try it. So there's this first derivative again. So you can see if we go through and apply the power rule again to each term, except for the constant, of course, ultimately you end up with 80x cubed plus 36x squared minus 30x. And we're not done. We're going to go and get the third derivative too. All right, we'll give a minute to catch up, and then we'll do the third derivative. All right. So once again, now here, there's no constants. We're just applying the power rule to all three terms. Okay, and you can see, yes, when we're done, we end up with 240x squared plus 72x minus 30. Well, you know what I think we should do, just for the fun of it, why don't we carry on? So my challenge to you is to calculate the fourth derivative, which, by the way, the notation gets very interesting here. If we keep adding primes, it starts to become unwieldy after a while. The fourth derivative is actually written like this, the Roman numerals. So why don't you go ahead, it'll be a piece of cake by now. Why don't you go ahead and calculate the fourth derivative of this expression, meaning you're taking the first derivative of this one. All right, just to see what happens. Oops. So I'll tell you what I'll do. Let me copy this to the next page. Yeah, making superscripts and subscripts is a little tricky in PowerPoint, but if you know what to do, you can get it. So that's meant to represent the fourth derivative. You're going to have 240x, and the exponent is 1 minus 1. And then now this is a constant. So, I mean, it's just 72x. So that's just 72. So you end up with 480. Oh, I made a typo here. Sorry. 40x plus 72. Well, what the heck? Let's do the fifth derivative, which is, as you can probably guess, designated with the Roman numeral 5. And once again, what are you doing? You're actually just taking, applying the rules one more time. So we end up with, now the 480 is it's just a constant times x. So that means that you'll just wind up with 480. And of course, the 72 drops out at 0. And so finally, now this is what I was saying before, if you do this enough times, eventually you have to reach zero. As long as the function is a polynomial, the sixth derivative would just be zero. So in this case, we needed to go all the way up to the sixth derivative to get to zero. Now, when we're doing optimization later on, you'll see that this is actually a very important detail. But for now, it's just enough to be aware that if you keep taking the derivative, higher order derivatives of a polynomial, eventually it'll go to zero. Okay, so that's that. Now we're going to move into a slightly scary area. We're going to be looking at derivatives of trig functions. Yes, they have derivatives too. It's not just polynomials. Trig functions have derivatives, but some of them are pretty straightforward and some of them are not. So we're going to start out with the two basic ones, the sine and the cosine, and you'll see to your great relief that their derivatives are very straightforward. Just as an example, you can see there that the derivative of sine x is just cosine x, and the derivative of cosine x is negative sine x. Now, by the way, there is a chart in the book somewhere where you can see them all together in one place, but we'll start here. And then we're going to try some examples in which we illustrate these, but we're going to use these in conjunction with the other properties that we already know. Okay. So in a lot of ways, when you're doing derivatives, you're often applying multiple rules at the same time. It's very rare that you can do just one of the rules. Often we need more than one, and sometimes we can use quite a few of them in the same problem, as also there's often multiple ways of getting at the same result, which imply different mixtures of the different rules. So just like anything else in math, there's almost invariably multiple ways of getting to the same results. So let's see what this first one is all about. What's the derivative of 5x cubed times sine of x? Now here, as I was saying, all of a sudden it turns out we need the product rule. By the way, I'm just dying to know what this looks like. Let's go see what Symbolab has to say about that. Sometimes, with these functions, you look at it and say, what is that going to look like? Is it again 5x cubed sine x? Oh my God. Well, that's just plain bizarre. But that's what it looks like. All right. Anyway. Oh, they're offering to take the derivative. Actually, I don't want you to see that because it'll give it away. So we're going to use the product rule. Okay, so I repeated the product rule right here. When you have f of x equals g of x times h of x, we just did this a little while ago. This is what it looks like. So since our function looks like this, let me just quickly sneak that in here. So we think of the g of x as the 5x cubed and h of x as sine of x. So down here, you can see g prime of x, we're using the power rule to come up with 15x squared, and h prime of x is the cosine of x, as we just learned. Okay, so now we plug these in, of course, to here. And then if possible, you may want to simplify it, maybe not. All right, so let's see what we get. Yeah, that doesn't look so messy. So that's the answer. And so of course, you notice we were using the product rule, but we also were applying the derivatives of this trigonometric functions. And yeah, there's no identities here that we can use to simplify it any further. If you really just like to simplify things, you notice, for example, you could factor out 5x squared, something like that. I don't see the point, but yeah, you could do that. Now, one reason why you might want to do this, though, is if what's inside parentheses is an identity that can be simplified, that's a different matter altogether. Then it really would make sense to do this, but not for here. All right, now let's take a look at this one. Oh no, the dreaded quotient rule. Yeah, that was bound to pop up again. So the function is cosine x over 4x squared. Of course, we're going to use the quotient rule, which we were just looking at a few minutes ago. So the numerator is g of x, the denominator is h of x. So why don't we start writing these things down here real fast. G of x is the numerator. And you might recall from a few minutes ago, we saw that the derivative of cosine x is negative sine x. And then the denominator is 4x squared. And so therefore, using the power rule, we end up with 8x. And now, of course, we just have to plug everything into that very complicated formula. But this is how we start. Okay, so usually your best bet is to write these out first. You can try to plug them in directly after you've had enough practice, but I think your best strategy is to just break it up, write down all the individual components and put them back together. And let's see, here it is. So there's the formula. And so I plugged everything in. And you can see it doesn't reduce to anything particularly simple. So, but that's it. That's all we have to do. Yeah, the only thing we really did here was that I just moved this negative sign and then I squared 4x squared is 16x to the fourth. And this negative was moved out here. Usually when they're negatives, you try to consolidate them all and bring them into the front. Otherwise, you're just asking for trouble. Also, I noticed that it's often common practice to have, whenever there's a mixture of trig functions and polynomials together, we tend to write the trig part last, but I don't think there's any real hard and fast rule on that. All right, now I did mention, so far we've only seen the derivatives of cosine and sine x. Let's see the rest of them. Now, for example, this one, you might be surprised to learn that the derivative of the tangent is the secant squared of x. Wow. I bet nobody saw that coming. And so what we're going to do here is try to figure out why. All right, so we're going to demonstrate why this is true. And just keep in mind, when we're dealing with trig functions, we often end up using convenient rearrangements of identities. Identities are really important with trig functions because they can often streamline our results into something much more, much simpler and make our lives that much easier. So you might recall, we went over this, I guess, Thursday. The tangent of x, actually, I think this was during the first week, the tangent of x is actually the sine of x over the cosine of x. All right, that's an important detail. So let's see what happens if I rewrite this. And then I take the derivative. Okay, so in other words, what I'd like to do is take the derivative of this ratio using the quotient rule. So this is our g of x, and this is our h of x. And as we saw just a little while ago, the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the negative sine of x. So that was the easy part. Now we get to plug them into that scary formula. And then even more interesting is looking for opportunities to simplify the results. All right. So when you look at it, you'll probably say, you know, that doesn't look very promising. But then all of a sudden, wait a minute. All right, so let me show you how this turns out. So if you just plug everything in, by the way, I just want to remind everyone, as far as the notation is concerned, and this can be very confusing. These all mean the same thing. Okay, just be aware of that. So anyway, if you notice in the numerator, we have this very interesting result, cosine x squared, sine x squared, cosine x squared, all over cosine x squared. Now, way back, somewhere along the way, in chapter 1, you might recall we reintroduced the so-called Pythagorean identities. There's actually 3 of them, but they're all based on the same idea. And what that one is this. No matter what x is, no matter what angle it is, whether it's angles, or degrees, or radians, or whatever, the sum of the squared sine and cosine always adds up to 1. That's, as you'll see, is going to be a huge deal here. So if that's the case, we can plainly see that we end up with this expression is nothing but well, how does that help? Well, let me just quickly remind you. But it turns out then, you can also write this as So therefore, what does this tell me? That when you bring these together, since the cosine is the inverse of the secant, this indicates that the same thing holds for the squares. So this is equal to 1 over the secant squared of x, or just secant squared of x. Now, that's why I said, so it doesn't seem obvious at first glance. But sure enough, that is correct. And we just proved it by a clever combination of the quotient rule and the Pythagorean identity. So like I said, you know, with the trig functions, you're always on the lookout for identities that you can slip in there. There's so many of them. In fact, you might recall that 1-B, or no, 1-C which was meant to be an overview of trig functions. There's a lot more stuff in there that we never covered. There's all kinds of crazy identities that you can take advantage of. Well, here we'll try to stick to the basic ones, but there's a ton of them. There's the half angles and there's the double angles. There's all kinds of nonsense. And then later on, you might recall, you don't really need them right now. There's also the arc sine, the arc cosine. There's the hyperbolics. There's all kinds of variations of these sine functions. Trig functions. All right, what else can we do here? Oh, let's take a look at the others. Okay, so that means leaves 3 more, and we're not going to demonstrate all of them, but you certainly could, if you felt so inclined, by replacing these with Pythagorean identities, or else the identities themselves. Now, there's the definitions, like, for example, you might recall that secant x is 1 over cosine of x. And you could rearrange these algebraically, and with the help of the quotient rule, you should be able to prove this. Okay. So then finally at the end, the cosecant, the derivative is negative cosecant x times cotangent. All right. Now you'll have access, of course, to all of these. I don't know if you'd have to memorize these even in the in-person class, but there's a chart in the book somewhere, and if not, it certainly is here. And so anytime you encounter something like, let's say this one, which looks like a catastrophe at first glance, but then you realize, wait a minute. Maybe it's not so hard. Now, let's say, for example, the first term. Now, of course, as always, we're actually using the sum rule here. You can think of this as g of x and h of x, and all we're really trying to do here is calculate the sum of the 2 derivatives. So as it turns out, we have an expression for this from right here. Okay, it's the cosecant times the cotangent. This is the tricky one, because all of a sudden we need the product rule. Oh, no. Okay, so how would that work? So for x tan x, let's remind ourselves what this thing looks like. So we're going to treat x as the g of x, and therefore its derivative is simply 1. H of x is the tangent, and as we saw a few minutes ago in the chart, the derivative of the tangent is the secant squared x, and of course we proved it as well. So now we plug these in. Now that's the second term. Remember, there were 2 terms here. Okay, so when we bring them together, this is our final result. Okay, so this is the result of the product rule. X secant squared x plus tangent x, which we proved here. And then this one, this is just the definition. Okay, this is right here. This is something, the definition is the derivative of the cosecant. And so that wasn't too painful, but we did have to apply the multiplication rule to the second term, x tangent x, but it wasn't that difficult. Well, now I'm gonna show you one of the most powerful results in calculus. It takes a while to get used to this thing, though. We're going to see it a lot as we go forward. So, we'll have to get used to it sooner rather than later. It will take a while to get comfortable with this thing, but we will need it quite frequently. And so what happens here is the final technique that we'll be learning in this chapter is the so-called chain rule. And it's applied to, of course, composite functions, which you might remember would be something like this: f of g of x, g of f of x. These are known as composite functions. And so this chain rule is used to come up with a derivative for a composite function. For example, what is the value of f prime of g of x? What is the value of g prime of f of x? For that, we need something more complicated than what we've been doing. And there are special techniques we can use to come up with our results. And this is, interestingly enough, this is where we run into the differences between the approach of Newton and Leibniz, which we mentioned the other night. Gottfried Leibniz in Germany and Sir Isaac Newton in England were both credited with inventing calculus. They both developed the ideas around the same time. They both eventually published their papers, so we can see when and how they were developed. But as it turns out, a lot of the notation that we use today is actually from Leibniz. Apparently, Newton's notation was more involved, and so mathematicians found that they preferred Leibniz's notation, and they stuck with it. But everything that's in Leibniz's book is in Newton's, and vice versa. And so this is a case we're actually going to, for the first time, explicitly use one of Leibniz's or some of his notation. And I think you'll see why, because it's a very straightforward approach. But again, it does take some practice to get used to this idea. So how does this work? Yeah, well, it looks terrifying already, doesn't it? We're going to assume that we have functions y, u, and g. So the composite function is f of g of x. But to make things even more complicated, y is a function of u, and u is a function of g. And so the consequence of that is that, well, this part we've seen many times before, it turns out that we can rewrite this as dy du times du dx. Now you can see, if you can think of these as canceling each other out, you can see why this must be true. But this approach can actually make things simpler for us. It's hard to believe, but it's true. And this is notation comes to us from Leibniz. I'll show you later on Newton's notation for this. And it just means we have to be a little clever to come up with a result without going through as much pain through very complicated formulas. So let me show an example of this. Now, we're going to see a very innocuous looking problem, which doesn't have to be solved with the chain rule, by the way. But we're going to do it anyway. So this is what I mean. So the function is 5x cubed minus 2x to the squared plus 3 to the 5th power. Now, if I wanted to really torture myself, I could actually figure out what I get when I multiply that function by itself 5 times, and then I can apply the power rule to each individual term. But that could take all night. So let's do this. Here's our clever strategy. U will be this function. We're going to define u to be what's inside the parentheses. Which means that we could rewrite y as u to the 5th power. Okay, now again, we're doing this because you'll see it's hard to believe now because it is going to speed this up a bit. Okay, so what exactly do we mean by that? Let's see. Let me copy these onto the next slide. Oh my God, I didn't realize that was going to happen. It messed up my superscripts. Yeah, I'll tell it. I'll just write them. Okay, so if that's the case, then dy du is just 5u to the fourth. We're applying the power rule to u to the fifth power. Okay, so dy du is 5u to the fourth. On the other hand, since u is 5x cubed minus 2x plus 3, du dx, again, applying the power rule to each term, gives me 15x squared minus 4x. So how does that help us? So that tells me, by the way, that my result is, so far, 5u to the fourth, 15x squared minus 4x. Now, at this point, what we have to do in order to avoid having too many variables floating around is we're going to replace the u with the value that we assigned it in the first place, okay? So what we actually have here is 5 times 5x cubed minus 2x squared plus 3 all to the fourth power times 15x squared minus 4x. And we're done. Oh my God. Now, what else could we have done? Oh, wait a minute now. Okay, so that's the final answer. So in order to avoid that, there's something else we could have done here. So let me just quickly grab the details back. And quickly remind us of something we saw a little earlier. Why it's the generalized power function rule. All right, I'm looking for it. Oh, here we go. So in other words, in this particular case, I could have just used this rule because you can see n is 5 and g of x is 5x cubed minus 2x squared plus 3. So therefore, g prime of x, 15x squared minus 4x. So plugging these in, it's the same, isn't it? It is. I'll just copy this to confirm it. So what this is showing me is that the generalized power rule is essentially a special case of the chain rule. Okay, in other words, the chain rule can get a lot messier than that. But when we're dealing with simple polynomials, then the chain rule will give me the same results as the general power rule. Okay, and in fact, to me, it's just a little bit more straightforward because you don't have to deal with dy, du, and du, dx, but it's good to know that the rule exists, okay, because we're going to see in the next example that, well, it's a good thing to have this because it can really save us a lot of grief. So again, if you have a polynomial like this, you can feel free to use the generalized power rule, but you can also use the chain rule because you're guaranteed to get the same results. But for more messy situations, then we'll certainly want to use the chain rule. Like, well, here's an example. You might not think so, but this is actually a fairly complicated problem. When you see it, you'll say, what if f of x is the cube of sine x, or sine x cubed? Oh no, what do we do now? Well, we don't have a rule for this, do we? When I showed you the derivatives of the trig functions, there were no rules for sine cubed. So what are we supposed to do now? Certainly the generalized power rule doesn't do us any good because that is defined in terms of polynomials. But we can still use the chain rule. So like I said, the generalized power rule is a special case of the chain rule for polynomials. This is not a polynomial. Polynomials do not include trig functions. They only apply to x's and exponents. By the way, a polynomial technically can only accept exponents that are non-negative integers. So this certainly does not qualify. So what can we do? All right. Well, first of all, as I mentioned earlier, just be aware that this notation is the same as this. They mean the same thing. They mean the sine of x multiplied by itself 3 times. How does that help? All right, well, let's do this. So remember the way this chain rule works. What we normally do with the chain rule is we look for something that can act as our u, something that is raised to another exponent. So let's try u. Let's let this be u. Then what this tells us is that f of x is very simply u cubed. Oh, now how does that help? Because the derivative is very simply dy du, du dx. Oh, by the way, f of x and y, of course, are the same thing. So I should have written this as y. What this tells me is that dy du, based on the power rule, is 3u squared. And since u itself is sine of x, du is cosine x. Du dx is cosine x. So I'm all set. I'll have 3u squared times cosine x. And since u has been defined to be sine squared, and we're done. Wow. So now something like this, I would imagine there might be ways you could rewrite this with trig identities, but It's so straightforward to do it this way. The only challenge really, like I said, is to look for the appropriate value for you. That really is the only challenge. Once you have a value for you, where when you're done, you want y to be u raised to some power or other. If you choose the u carefully, then you'll end up with that exactly what you're looking for, and you'll end up with your results. Now, if you choose badly, what will happen is, as you start applying the rule, the function will actually become messier than what you started out with. And that's how you know something's wrong. So then what you do is go back to the drawing board and you try something a little simpler. Okay, and eventually you'll hit onto the right one. And then you'll know because the answer is fairly straightforward. Whoa, that was complicated. All right. Now, by the way, the book has very kindly provided us with a nice little chart, so we don't have to keep doing this over and over again. Let me just show it to you real fast. And this is already includes the g of x. So what they're basically doing here, when you see a g of x here like that, that tells you that they're actually using the chain rule. So the derivative, for example, of sine g of x is cosine g of x times g prime of x. So you might contrast that with what we saw earlier. When we just have x here, the derivative was just cosine x. But once it turns out that it's now the sine of a function of x, that's when the chain rule has to get involved. And so instead of just cosine g of x, we also need this derivative g prime of x. So whenever the chain rule gets involved, we're always going to wind up with a derivative of the function g of x. And if you want to use Gottfried Leibniz's notation, the one on the right, d sine u is cosine u du dx. It's the same thing. Wow, look at all this. Okay, well, I think you're probably ready to fall out of your chair, so let's have a break. Now, when we come back, we're going to look at something interesting here. We're actually able to take derivatives of inverse functions directly. It can be a little messy. We'll do that. And then we'll dive into the appendix and see what other goodies are hiding in there. Okay. So I know that you're all a little weary now. So that's okay. We'll get some refreshments. And when we come back in about 15 minutes, we'll finish up this section and then we'll dive into the appendix. Okay. All right. All right, I guess we're all set now. So the last part of this section is the derivatives of inverse functions. Now, of course, we briefly went over this in the first chapter. Inverses are functions where essentially you can think of them as one is offsetting the other one. So just as a quick reminder of inverse functions, f of x equals x squared, and f of x equals the square root of x are inverse functions. And that's because if you were to take, for example, the square root of x squared, it gives you back x, or if you square the square root of x, it also gives you back x. So in other words, it's almost as if they're basically offsetting each other. And the notation that we normally use for inverse functions is that f inverse is written as f minus 1 of x. Well, it turns out that there's a rule here that we can use to solve directly for an inverse. What I mean is the derivative of an inverse. So this is what it looks like. Now, sometimes using this formula can be easier than directly taking the derivative of a function. If, let's say, the inverse has a simpler form, it might be worth our while to use this approach instead of trying to solve for the derivative directly. So the derivative of f inverse of x is 1 over f prime of f inverse of x. All right, well, that looks very complicated. So why don't we look at a couple of examples. And well, first of all, too, I just want to mention that you can also rewrite this if it's simpler as g of x. In other words, in some books, instead of writing f inverse of x, they'll just replace that with g of x with the understanding that these mean the same thing. All right, so let's just look at this case. So let's just say we have f of x is 2 over x minus 1. It turns out that the inverse is, and we'll write it here using that same notation, instead of using f inverse or f minus 1 of x, we'll simply rewrite it as g of x. And that turned out to be x plus 2 over x. Now, just in case you're wondering how we went from here to here, there's a relatively straightforward way of doing this. And there's also a simple way of proving that we have done this correctly. So let's just do that real fast, and then we'll get back to the derivatives. So if we started out with f of x equal 2 over x minus 1. So what we can do is rewrite this as y equals 2 over x minus 1. And then what you're actually going to do is reverse the x and the y. So you'll have x equals 2 over y minus 1. And then we'll solve for y. So in this case, you could cross multiply x times y minus 1 equals 2. Xy minus x equals 2. And then I end up with y equals 2 plus x over x. And that's exactly what was here, except that it's written as x plus 2, but it's the same thing. So in other words, starting with 2 over x minus 1, we were able to prove that the inverse would therefore be 2 plus x over x. And if you really feel like it, you can prove it that you've done this correctly by doing the following. Okay, so in other words, you could write it like this. If both of these conditions are true, that means that G and F are inverses. All right, so let's remind ourselves that in this case, we saw that starting out with f of x equals 2 over x minus 1, we determined that g of x, or the inverse, was 2 plus x over x, or at least we think so. All right, we use the technique, and now we just want to make sure that we did it correctly. So f of g of x, oops, would therefore be 2 over g of x minus 1. Now with these, you've got to be careful sometimes. It would be very easy to make an algebraic error with something like this. Whoops, sorry. When you consolidate these two into a single equation or a single ratio, 2 plus x minus x leaves us with 2. And 2 over x is the same as 2 times x over 2. Okay, so this condition has been met. Great, now let's do the opposite. Let's see what happens when we take g of f of x. And if we did everything correctly, that should result in an x. All right, here we go. So just a quick reminder, f of x is 2 over x minus 1. G of x, 2 plus x over x. And so we're trying to see now what happens when we get g of f of x. So that's now over here is g of x, 2 plus f of x over f of x. So I'll have to consolidate these terms in the numerator. So let's see. 2x minus 2 So I'll rewrite it as 2x over x minus 1 times the inverse of the denominator. These cancel, these 2's cancel. Oh, yeah, there we go. So this one worked as well. So what we just did is prove that these two are, in fact, inverses of each other. Great. So now what we're really after, though, is we're trying to take the derivative of g of x. That's ultimately what we're after. Okay, so what we're trying to do is find out what is g prime of x. Okay, so in other words, we started out with f of x, and we're interested in g prime of x. So this is the formula. Okay. No, here it is. Okay, so just as a reminder, this is f of x, g of x is, again, 2 plus x over x. So we need f prime of x, and we're going to evaluate it at g of x. So we're going to use the quotient rule here. And so g of x is 2, which implies that g prime of x is 0. from the constant rule, h of x is x minus 1. H prime of x is just 1. Okay, the derivative of x is 1. The derivative of any constant is 0. So remember how this works. Quotient rule says to do this. Whoops, h of x squared. All right, so we have x minus 1. Sadly, I'm going to run out of space here, so let's do this. This is supposed to be the solution. What we're trying to do is prove it, that it's right or wrong. All right, that should do it. All right, so we'll start plugging in numbers. So of course this drops out. We end up with minus 2 over x minus 1 squared. All right, so far so good. That is in fact f prime of x. Now, what we want though is f prime of g of x. So f prime of g of x would be, therefore be this. And if you recall, g of x itself is the inverse of f of x. Okay, so this is where we are. G of x, that goes in here. Oh man, so we're not quite done. Algebraically, there's a lot more algebra here. So let me just skip to the next slide, but you can see where we're going. And if you plug all that in, well, this is the final result. So it was kind of a mess, but we did manage to get it done. So now, of course, the original g of x was x plus 2 over x. In a case like this, g prime of x would have been much quicker and easier if we simply used the quotient rule. But again, sometimes this works out better and sometimes it doesn't. Every situation is different. Sometimes using alternative approaches can help. Sometimes it's easier to just use the basic rules. Okay, so because this one is a relatively simple function, the quotient rule is probably the best way to go because it avoids the need to calculate inverses. But for certain cases, this would make things a lot simpler. So that depends on what problem we started out with. It's just good to know that this works as well as using the quotient rule. All right, so finally, this is what I call chapter 3. What's coming up next is the so-called appendix, which I just finished today. And this is where we're going to finish up chapter 3. We have a handful of important topics to cover here. Some of them straightforward, some of them not so much. But we're going to start here with this simple idea that the power rule itself does not necessarily have to be applied to cases where the exponent is an integer. It's also possible to apply it to what are called rational exponents. And of course, a rational exponent or any rational number itself is just the ratio of two integers. So like, for example, 3/5 is rational. radical 2, it turns out, is irrational. It's not possible to express this as a ratio of two integers, pi, the most famous example. So we're not going to apply the power rule when the exponent is either radical 2 or pi, but we will use it when we have either an integer for n or possibly a rational number. Now, the only issue we have to watch out for here is that it gets a little messy. Now, this is what we're used to seeing. Okay, so this is not so bad. But let's say instead we have something like this. Instead of x raised to the nth power, it's raised to the 1 over n power. Well, the basic logic behind the power rule hasn't changed. Okay, you're multiplying by the exponent. Here we have x, and here the exponent is, so we have 1 subtracted from it. And we can simplify that a little if we need to. Actually, we don't. It's fine the way it is. So we'll leave it like that. And so basically nothing's really changed. It's just that the exponent was a fraction. In the next example, we'll see something that's a little bit more general. And this time, no, it's really hardly any different. This is what's changed. Instead of 1 over n, we have m over n, where of course m and n are both integers. And so again, you just multiply. You start with m over n, you multiply by x, and then in the exponent we have the exponent that we started out with minus 1, and that's all there is to it. So the case we had a second ago was just a special case where m is equal to 1. So really, this is the rule right here. All right, let's take a look at a couple of simple cases. Okay. All right, how about this one? F of x is x to the 2/3 power. So using the rule, the power rule for rational exponents, we have 2/3 x to the 2/3 minus 1. And of course, 2/3 minus 1, very simply, can be written as 2/3 minus 3/3, which leaves us with minus 1/3. So it's not hard at all. But it's good to know that this applies to fractions as well. Also, I just want to point out that this is equivalent to this. Okay, in other words, whenever you have x to the negative n, it's the same thing as 1 over x to the positive n. Very good. All right, now how about this second case, m over n? Well, actually, this is the same. Sorry, they're both m over n, but this one is a negative value in the exponent. So we multiply by the exponent, and then we subtract 1. So here we do have to watch it because we're subtracting from a negative number. And so the exponent is negative 9/4. Negative 5/4, x to the negative 9/4. Okay. So in the next example, we're going to do exactly the same thing, except that we're going to evaluate at a specific point. Okay. So let's say, for example, we're looking for the slope of the tangent line. Okay, actually, this is wrong. This should say slope. It says equation, but it should say slope. We're only really interested in the slope. We got the function f of x equals x to the 4/5. We'll evaluate that at x equals 6. Now, just for the fun of it, why don't we see what this thing looks like in Symbolab? I'm not sure what to expect here. This is a very, okay, interesting case. So it's x raised to the 4/5 power. Oh my God. Well, now that's interesting. I wasn't expecting that, that's for sure. It is like just like the absolute value, except that it's not two straight lines, is it? No. Very interesting. All right, but anyway, we're looking for the tangent line where x equals 6. That would be right about here, let's say. So how do we do that? Well, we take the first derivative as always, which it turns out to be 4/5 x to the negative 1/5. And then you replace the x with 6. And it turns out that I rewrote it, if you notice, as 4/5 times the 5th root of 6. That turns out to be approximately 0.559. Okay, so this is exactly the same type of situation, except that we solved at a specific point. Okay, now we're going to dive into an area of trigonometry that you've run into before, but it's probably been a while. We're going to be looking at the so-called inverse trig functions. So what do we mean by that? Okay, so for example, we have what we call the arc sine, which can be written as either sine minus 1 or arc sine. It's written as sine minus 1 because it is an inverse. But, well, anyway, but a lot of books prefer to write the words arc sine because they want to make it very clear that unlike something like this, these are not the same. Oh, actually, I forgot the x. It means something completely different. I'll tell you why. A part of the reason for that is because when you take a sine, let's say you took the sine of, I don't know, let's go to Symbolab for a second. Now let's try a more interesting one. How about 90? Okay, so what is this all about? If the sine of 90 is 1, now keep in mind 90 means 90 degrees. The arc sine of 1 is 90 degrees. So in other words, the sine gives me a numerical value with no units. The arc sine is measured in either degrees or radians. Okay, so in other words, what it's really saying is, we know that the sine of 90 is 1. The arc sine, what it's saying is that the value of 1 has a sine of 90. So with the sine, you're taking an angle and turning it into a ratio, basically, of the opposite over the hypotenuse. With the arc sine, you're taking that same ratio and converting it back into an angle. So when you ask, what is the arc sine of 1, what you're basically saying is which angle has a sine of 1? And the answer to that is 90. So it's a very strange idea, I guess. We just have to remind ourselves how this works. But essentially, think of them as just giving you the same information coming from the opposite direction. In the first case, you say, give me an angle and I'll give you a ratio. In the second case, you're basically saying, give me a ratio and I'll give you an angle. So you can see the inverse of this. If by this sine minus 1, we mean the inverse, that would be 1/1, which is x. So that's why a lot of books prefer to use this notation, but you still sometimes see it written like this, but with the understanding that when this is applied to a trig function, it's not an inverse as such, it is the arc version of that angle, of that function. And of course, similarly, we have an arc cosine. We have an arctan. We have an arc for all of them. And there's a nice little chart here that's the book is giving us to remind ourselves what exactly is going on here, at least for these three. So just a quick reminder that you're taking a sine of an angle of some kind is a ratio, as are the cosine and the tangent. But the arc sine is an angle, arc cosine is an angle, the arc tangent is an angle. All right, so here I put together some actual numerical examples. Again, just to reinforce the idea of what this means. For example, if the sine of 30 is a half, the arc sine of a half is 30. The two are, you're basically reversing the two. Okay, then we have a cosine example. The cosine of 90 is 0, which implies that the arc cosine of 0 is 90. Again, they're just opposites of each other. And then one more, let's do a arc tangent. Since the tangent of 45 degrees is 1, the arc tangent of 1 must be 45 degrees. Okay, now, as it turns out, again, the book has given us a chart showing us the derivatives of these functions. Let's take a quick look. And again, no, I guess in reality, nobody would expect you to memorize all these, but just know that this chart is here. And if you're really interested, the proofs of these formulas are actually in the book. If you feel like I need to know why is this arc sine's derivative 1 over 1 square root of 1 minus x squared, the proof is in there. They'll show it to you in great detail. But for our purposes, this is enough. And so when you run into these problems that involve arc sines or cosines, whatever, you at some point may need to resort to this table. Yeah, some of those later ones are pretty scary looking. So like, for example, what if there's a question in the test and it says, what is, if f of x is the arc cosine of x, what is f prime of x? And you say, oh, I will go consult with my handy little chart. And why, there it is on the bottom, minus 1 over absolute x times the square root of x squared minus 1. Now, what I would like you to know is that these can be extended with the chain rule. Let me just show you a quick example, which I guess after a while you start to get suspicious. Whenever you see new functions, you start to wonder, can we use the chain rule? So like for the sine, instead of just x, if we have g of x, what ends up happening is that we have the x becomes g of x, and then we multiply by g prime of x. And you'll see the same pattern for all of them. In other words, if it's not just the sine of x or cosine or whatever, the x is replaced with g of x, and then at the end you multiply by g prime of x. I don't think the book has a table, a separate table for that. I'll look for it. But they do have this. Just be aware that if you're taking, let's say, the arc sine of 3x squared or something like that, then you have to use the chain rule, and this is how it would work. So I did mention before, the chain rule will show up in a lot of different places as we go along, and this is one of them. Taking derivatives of arc sines and arc cosines and all the rest can require the chain rule if we're taking the arc angle, let's say arc sine of a function of x, not just x. And in fact, I think we have an example right here. Here we go. What if it turns out that we're looking for the arc? We have the original function is the arctangent of x squared. What then is the f prime of x? Now, the tangent in this chart is and that's all there is to it. It's that simple. You can see it right there. But this is not x, is it? It's a function of x. So all of a sudden, that changes everything. Now we need to replace each x with g of x, and we need that g prime of x. Okay, well, let's see. Well, it turns out then that we can think of this if we decide if g of x is x squared, then of course g prime of x would just be 2x. And so we're just going to wind up with oh, that wasn't so hard. The tricky part was just recognizing that this is now the arctangent of a function of x. And therefore, by using the chain rule, we need to have not just g of x expressed here, but we also need g prime of x. Oh, wait a minute. No, I just realized I goofed it up, didn't I? Yes, I'll tell you why. Because g of x is x squared. We needed g of x. This is my fault, sorry. Now we're all set. You see what I did wrong? The function is 1 plus x. In order to turn this into g of x, yeah, that's right. That's more like it. So in other words, down here, what I should have had is this. Now we're good. Much better. Okay. So yes, in spite of that, so in the next slide, it's all written out more clearly. You can see that since g of x is 2x, sorry, no, it isn't. It's x squared, which implies that g prime of x is 2x. So we're going to end up with 1 over 1 plus x squared times 2x, which we can simplify to 2x over 1 plus x to the 4th. All right. Now this next one's kind of a mess. And then now when this part is done, we're going to introduce this very interesting idea. Well, maybe I'll save that for tomorrow. I'm looking ahead to see if there's anything. There's still some very intense stuff coming up here, but it's very, very important. Ooh, baby. Okay, I'll tell you what. It's 8:54. There's no point in pushing this. We'll stop here, I think, because what's coming up next is fairly involved. And then tomorrow we should be able to at least start chapter 4, where we're looking at applications. And that is where we get to introduce some really important ideas like optimization, for example. So, all right, anyway, I think this is enough for one night. Nothing's due tomorrow or anything like that. As usual, we'll just have something to do on Thursday, and we'll take it from there. So if there's no last minute questions, we'll pick it up right here tomorrow, and then we'll start chapter 4. All right, so I hope that wasn't too scary. and I'll see you tomorrow.
Thanks, Professor. See you
Hey,
tomorrow.
you're welcome.
Good night.
Good night.
Thank you.
Bye.